back to the exercise that we did last time, where we had multiple knife edge fraction. And as you can possibly imagine, the next question is, next problem is to solve this problem using the Day-Group method. We calculate the additional attenuation using the obviously we already discarded this, but this is will be automatically discarded if you apply the Day-Group method instead of the Peterson method. So try to solve it. If you have questions or about theory or other exercises that we did before, you can ask them now. I'm here, so you can take the opportunity to. The Day-Group method is also called the main edge method, as you possibly remember from here. Well, you remove this one, so you calculate the distance between this one and this one. Yes, like you are only one edge.
For example, that
Person, yes. All the line is different, but the equations are the same. The other are the same as the other exercise that we did last time. So this is let me find, yes, 10 yes, 10 meters. This is 20. This is 5. This is 15. Exactly the same. This is done to compare the results that you get when you use different values. Okay. Now, as you remember, the main edge method requires the identification of the main edge. And to do this, we have to consider one edge at a time, ignoring all the other ones. Now, we already discarded this because it's negligible. So you can consider that, but it will be even negligible contribution. So really, the only edges that we have are edge A and edge B. Edge B. What is the dominant edge? Well, it depends on the Fresnel-Kirchhoff parameter that we have to calculate. And to that purpose, we need to calculate, first of all, those distances, the height with respect to the baseline that is touched. And let's call this now. There are several ways to calculate those quantities. You can use, for example, a proportion between those two triangles, this one, and this one. Those are proportional triangles. Or you can use, like we did before, we can find the equation of a line that passes between those 2 points. Like we did before. I will follow this method, but you can use proportions or trigonometry. You can calculate this angle, for example. Another way, you can calculate this angle and then calculate those sides with trigonometry. So you have several choices. All of them are good. I take the most complicated way. I leave you the easy way to do. To try this at all, So you can write, I'm looking for the equation of the dashed line. And so we force the line to pass between this point. And so we write tan equal to B. And we force the line to pass through this point. So we write something 0 because y is 0 at that point is equal to 2000 times x plus b. Times 2000 times a plus b. So we get this equation at the end. With the minus signs. Minus 5 times 10 to the minus 3x plus b. That's the equation of that line. So we can call this epsilon 1. You can call this epsilon 2. So indeed, for x equal to 500, first point, we find epsilon 1 equal to 7.5. This means that H1 is 20 minus epsilon 1, 12.5. Then we move to this other point, and we have 1,500 for x. It means we have 2.5 perpendicular segment. Minus again 12.5 meters. So the two heights are the same. This does not mean in principle that the Fresnel-Kirchhoff parameter will be the same. So let's calculate them. Will be h1, that is 12.5, square root of 2 times 2000 divided 0.33, that is the wavelength. I'm not rewriting the equation, you have the equation on your book, on your notes, times 500, 1.58. This is the first Fresnel-Kirchhoff parameter. And then we calculate the second one. And we discover, to our surprise, they are exactly the same. So there is, which is the main edge? That's it, the decision is left to us. They are exactly the same. They have the same Fresnel-Kirchhoff parameter. So we just choose one at random. Let's choose this one as a main edge. Since the two Fresnel-Kirchhoff parameters are the same, we don't have a leading main edge. So we just decide. So we took one. We took B, for example, and it doesn't matter. And if we calculate, first of all, the contribution from the main edge, let's call this losses due to B. We now apply the procedure that is standard. Okay. Now we consider this as a main edge, so we consider the diffraction due to this geometry. So we have I wish I had it here. Yes. H first 2 is equal, we already calculated that, 12.5 meters. So the parameters are the same, so we can use, we don't calculate them again. This is 1.58. That gives you an attenuation due to HB if you use the table of 70 dB. And this is the main edge. And then we have to introduce the contribution from the right and left main edges. Now, on the left there is nothing. So there is sorry, on the right there is nothing. There is no right main edge. On the left, we do have the left secondary edge, and for this one we have to calculate the losses, but taking into account now a different. Now we are calculating losses between the main edge and the left edge. And those must be computed by calculating this baseline and that height. Now, for the left edge, if you do the calculation the way you like, you will find for this value, I'm not doing the same things again, you will find H to be equal to 8.33 meters. We already calculated that in the past exercise, where we used the AP method. Then you have a distance of 500 meters on this side and 1,000 meters on this side. We already calculated that, but let me remind you that what we find is divided lambda 0.333 times 500 times 1,000. And this is going to be 1.12. And this corresponds to losses to the left edge of 15.3 dB. The same value that we found in the previous exercise because the geometry is the same. So total losses, total or extra losses are the losses due to the main edge plus the losses to the left edge, 17 plus 15.3, 32.3 dB. Slightly different from the value that we found last time with the other method. Not terribly different, a little bit higher. With the Epstein-Peterson method, we find 30.something, 30.6. Now we find something slightly higher, not terribly higher. Questions? Yes?
You use the interpolate grade for
this.
For this.
You can use the approximation, or you can use the graphic.
I understand the graph, but the equation for describe this.
For this.
Yeah.
To go from here to there.
Yeah.
Yes. What's wrong with your question?
How to describe this equation for compound already?
I project the equation. Also because I need a projector for the next exercise. Should be back soon. Okay, in the meantime, let me get this. Can I wipe out in the meantime that my computer wakes up? If I can eventually, yeah. Okay, those are the equations. So, you have to identify the one that is relevant. In this case, we have V of 1.12. So, it's between 1 and 3.4. And you have to use this equation. You just have to replace here the V value and then calculate this equation. Okay, enough with for the moment with scattering. Rural propagation. Now we apply the next exercise. We apply the ITUR model using the graphics. We don't use the algorithm of the. But we just use the graphics that I gave you. I project the graphics for convenience. Now, the exercise is calculate the median field strength. I would like to have the result in dB with respect to 1 microvolt per meter. Let me see if this is better. For the following geometry, at 100 kilometers of distance. Frequency frequency 100 megahertz. Power, fixed power 10 kilowatt. Antenna gain is I need an antenna gain 10 dBi. X antenna, the antenna of the transmitter is on a hill at 300 meters above sea level, and the receiver antenna is on at 1.2 meters standard antenna, standard height. To do this, to perform this calculation, we have to identify first the relevant ITU table, ITU graphics. And by chance, this is it. It is 100 megahertz line path 50% of the time. Now, the way we have to proceed in this exercise is, as we have seen before, as I said before, first find free space field intensity. First, then work out, calculate the distance between the free space limit and the curve that refers to the real situation. So you find what is the difference in dB between free space and the relative curve, and then you reduce the value that you found in free space of that amount. That's the best way to do it. Calculate free space, find out from these graphics what is the distance between free space and real situation, and then reduce of that amount. You see a dB scale on this. Reduce of that amount the free space value that you have. Okay? You should have the graphic because I send it to you. So please try and solve this problem. I switch this off so you can, if you don't have more, it's not very readable. But if you don't have it, you can come and look at the picture to find out the. Find that start to do at least the first point, like finding the free space situation and try to find out how to read those graphics.
Es como el triple de bocha. Y es una relación de publicación en Facebook. Esa bocha es como el triple de bocha. Es más alto. Porque no le gusta que la plástica. Oye, ¿qué te sucede? Mira. ¿Qué está pasando? Estamos ¿de qué? Porque por ejemplo mandó a la Biblia no me llegué aquí. Sí, gracias. Ya me está bonito. Pero dile tú, pues. No, porque yo ya le pedí más. Le pedí el pedí. Yo también lo pedí. Yo se lo pedí. Y hay que hacer otra vez. Sí, y aparte ahorita le dijimos que comprar un juego. Pero ya con la plata del man. O sea, el Play lo compré el man, pero yo me lo voy a traer. Es un favor. Y ahorita es otro favor porque le pongo un juego. Que lo compré el man. Y ya lo gastamos. Y ya pidimos, pero ya le pedimos los juegos. Y no le pedimos un juego. Pero lo pegas sin oye, tomé. Pero tiene que mandar la plata. Ya saben que va a ser el caso. Sí, pero la mano es muy plata. Se va a gastar la plata. No, es que una cosa es tener la plata ya. Yo te digo porque cuando tú te vas de viaje, se te gasta toda la plata. Y te quedas hasta negativo. Empiezas a pedir la cifra 35 euros que no crees en el Estado. Primero de diciembre. Y si yo le pido y le mando la luz, ¿Qué pasa para mí? Si te pedí tus dos cakes, yo no. De hecho, pero que me he hecho los 15, pero
Ya, pide la china un cromo.
yo no lo había pedido.
Y yo te doy la plata, yo te doy la plata.
Mañana que le traje le
Sí, son broncas también, clávale vacaciones.
Pero ya tienes el profesor.
¿Cómo?
Se me dice de nada. Aguanta. Tienes el. ¿Qué tienes tú?
¿Qué huevada? Y el televisor ya lo tengo tratado de ocupar.
Qué bueno, oiga.
¿Cuánto pagas?
¿Sabes qué dice? El plan de cable y me subí $1.000.000 al internet. ¿Cuánto pagas? O sea, yo pagaba 60 y luego sumando ahí por ahí, se estaba mal y se sumaba. Ya sé, por qué te voy a o sea, no se puede pasar lo que nadie va a hablar. Sí, yo también y bajé uno de
Okay. Now,
Y este es lo sucio.
the first step is easy because, well, everything is easy really.
Bueno.
Okay, free space. Okay, we can calculate first the incident power density, like transmitted power, gain of the transmitting antenna, divided for distance squared. It is 10 kilowatt is going to be 10 to the power 4 times factor 10 NDVI is a factor 10 linear divided and if you do the math you get 7.96 10 to the minus 7 back. That's the power density. But we need the absolute value of the electric field. So we can start from this equation that tells us that there is a precise relation between the electric field and the power density. And when we solve this for the absolute value of the electric field, that is the square root of whatever times 377 ohm, that is the free space impedance. And if you put the number, you get 0.0173 volt per meter in free space. Since we are asked to calculate this quantity in dB microvolt per meter, let's already convert this into dB microvolt per meter. We can do this in 2 steps. This is going to be 173 power 6 microvolt per meter. And then we can calculate the value in dB, like 20. That free space, this is not the value that we will actually receive on the ground. To calculate that value, we can use this graphic by First of all, identifying the distance, 100 kilometers. That's the distance that we are interested in. And then we have to identify the curve that is relevant relative to the antenna height, transmitter antenna height. 300 meters, so is this curve here. The third, 1, 2, 3, is this curve here. You will appreciate it more precisely on your version. So, at 100 kilometers, what is the distance or the difference between our actual curve and the free space? Is 10, 20, 30, say 37 dB. 37. So the actual signal will be 37 dB. That is almost a factor 10,000, almost. It's 15 is 5,000, I think. Smaller than the free space value. But the answer is very simple, because we already had the value in the dB common per meter. So we just subtract 37. And we get the answer that is 47.7 with respect to microvolt per meter. Okay? That's the simplest way to use those graphics. Without you just have to ignore the absolute value here. You just have to work the difference between those values. It's the safest way to use it. Questions? If there are no questions, it means that you perfectly understood how it works. It means you are ready for another exercise of the same kind. Yes.
I use another equation for this model. 9 minus electric field plus 20 losses.
Then we give you the value of losses. Then we give you the values of losses in this case, and then yes, if you have losses, then you can use losses to calculate.
I use this equation and minus the distance of the losses.
How is it? Yes. Yes, you have to look at it. You have to identify the point, and then you use this value as a unit value.
It's the same.
Yes. Yes, please.
At the beginning they use the gain
10. No. In this case, 10 kilovatios. Always use linear values.
Porque eso no está, es que eso no está para 1 kilovatio.
By chance, 10 dB is a factor of 10 in linear scale. Other questions? Okay, so you know everything, so you will be able to answer to this exercise immediately. Calculate power needed to guarantee a coverage of 50% of the points. So we are still using the graphic, 50% of the points. Again, 100 megahertz, so we don't change the graphic. 100 kilometers of distance. TX antenna height, this time is 600 meters. Minimum field required at receiver. (30 dB microvolt per meter). So this time we work the other way around. We know what is our target field strength at the receiver. Please know that if you look at the IQR recommendations, when you have to design, for example, an FM broadcasting network for FM radio, you have to guarantee a given level of field strength. So you have to design to determine your transmitted power starting from the requirement. Like in this example. In this example, we are fixing the field that we want to have at 100 kilometers of distance. You have to tell me how many watts we need to use to guarantee that level of service. Now you should know how to use this graphic.